Okay, now we're going to talk about why Stokes' theorem actually works. And so this is a proof that I don't think is standard, but I think it's a little bit quicker than you might see. There's no calculus actually. All it does is uses Green's theorem. So the idea is it follows from Green's theorem, surprisingly, even though Green's theorem is the flat version. So here's the idea. Every surface is locally flat. Right? So it's just like saying that every curve is locally flat because you can zoom in and find pieces. So it's approximated by line segments pretty closely as long as the segments are small. So in the surface case, you might create a patchwork quilt like so. And so now to illustrate my point, let's just start with two patches. I'll call this S1 and S2 for the two surfaces. And the total will just be, of course, S. So let me just recall Stokes' theorem. If we take the integral over S of the curl dotted with the area vector, then this is equal to the closed line integral of the original function in true fundamental theorem calculus style. So, I'm sorry, not dsdr. Okay, so here's what we're going to do for our patchwork. We're first going to split the integral. And we're going to apply Green's theorem on each patch. And that gives us a line integral. Because remember, each patch is flat. And you know what the integrand should be. It should just be f dot dr. I'm lazy, as usual. So now we just need to combine them somehow. And that's what we want. We want f dot dr on the boundary. So the whole point is, how do we combine these two things? So let's just redraw the patches a little bigger. And I'm going to separate the boundaries a little bit to show you what's going on. So we have two sets of line integrals here. They're both positively oriented. So I need to draw these things counterclockwise. But here's the thing. On this middle segment here, notice we have a negative sign. It's going in the opposite direction. And we have a positive sign because that's just the regular direction. So we actually have these two things cancel. It's the same thing being integrated, but they're each going in opposite directions. So we have cancellation. In other words, plus and minus, they yield 0. So therefore, if we combine these things, we end up with just the rest of the curves. And that's just the original boundary. This was two line integrals, but we end up with a single one due to this cancellation. And so that's Stokes' theorem for this curved surface, which is just two patches. So now if we want to do any number of patches, you can see it'll work just as fine. So now if you want to do any curved surface, you'll just approximate it by a quilt. Right? So you approximate it, and now you take a limit, and you should end up with a surface after you take that limit. So Stokes works for patches, and after you take that limit, you get Stokes on the curved surface. So it shouldn't be that surprising it works. But what I swept under the rug is the following. Then now I'll explain this a little bit. Why does Green's theorem actually work on these patches? So why does Green's theorem work on tilted patches? Notice that these let's suppose that this one was flat. So in other words, it's a XY plane. Well, surely this one's not. This is not in the XY plane. So this is not planar. So why does Green's theorem work on S2? So that question, it follows from this. So this follows from the integrand. So let me just write those out, and I'm going to use the 3D integrands, not the qx minus py. I will not use this one. I want to use instead the curl dotted with ds, and that's the left-hand side of Stokes theorem, or Green's theorem in the 2D case, and the right-hand side is f dot dr. Notice that these are two dot products. And they're of vectors. Obviously, we're taking two vectors in each case, and we're taking dot products. So remember, the dot product is a dot b. And so here's the idea. These stay the same under rotations. Right? So if I just draw really quickly two vectors, and now I'm going to rotate these things in space, then what happens is these vectors change. But observe that their angle stays the same. And the lengths are the same. So if we remember that the dot product is simply AB cosine theta, it's going to be the same after rotation. So if we rotate S2, let me just draw it here. So if we rotate S2 to an XY planar patch, then the integrands stay the same. Because these are just dot products of vectors. Okay, so what I'm saying is, if I start off with S2 del cross F ds, what I will do now is just rotate this to a flat or xy flat patch. And it will still be of this dot product. And so now I'll just apply Green's theorem. And so now I'll rotate back. Because again, these are just dot products. Okay, so all that's going on here is that once we found this this good representation for the qx minus py, we actually are allowed to just rotate it now. And so that freedom we get from rotation, that's why we're able to patch these things together. So this is, I think, a little simpler than actually crunching through the calculus and taking all partial derivatives and stuff like that. But that proof is also available. Like on Wikipedia, I think they do go over that. It looks really messy. So I hope this was helpful. Thanks for watching.